Hello, everyone. Welcome to Temporal Graph Reading Group for October 24th. And today we are glad to host um, Alessio Gravina. Um, and I will start with the speaker introduction. Um, so Alessio Gravina is a postdoc researcher at the University of Pisa, Italy. He received his PhD from the University of Pisa in 2024 with a thesis on graph deep learning models inspired by dynamical systems and neural differential equations. He holds a master's and a bachelor degree in computer science from the same university, and he has been a visiting researcher at Huawei Research Center Munich in 2023 and at the Swiss AI Lab in 2022 and at Stanford in 2019. While he also won the Fuji AI NLP Challenge in 2018. His interests are in the area of deep learning and machine learning for graphs, with a special focus on differential equation-based graph neural networks. So I will hand the mic to you.
Yeah, thank you, Andy. Welcome. Today I'm going to present my one of my recent works titled Long-Range Propagation on Continuous Time Dynamic Graphs that has been accepted at ICML 2024. Graphs are a highly expressive abstraction for modeling entities and their relation. And they can be defined in both the static domain and in the temporal domain. And in the temporal case, graphs are referred to as dynamic graphs. And as I think you already know, similarly to static graph, a dynamic graph is a tuple, but here all the elements in the tuple are function of time t. So we have that, for example, the V provides the set of nodes which are present in the graph at time t, while the calligraphic E, the edges that are present at time t, and X and E, the node and edge features at time t. And we can identify two types of dynamic graphs. So we can have discrete time dynamic graphs or continuous time dynamic graphs. The first is a sequence of static graphs called snapshots, and each of them provide an observation of the entire graph at some point in time t. And usually the interval between the snapshot is constant over time. While a continuous time dynamic graph is a stream of events that can appear at any time. And so for this reason, they can be seen as a more fine-grained version of discrete time dynamic graphs. And this event can be interaction events where, for example, new temporal edges are created, or node-wise event, or deletion events where we delete a node or an edge. And deep graph networks, also called graph neural networks, have emerged as a family of deep learning models that can effectively process and learn such structured information. And in particular, deep graph networks turn out to be extremely effective in processing this spatiotemporal evolution of dynamic graphs. And depending on the architecture that is behind the deep graph network, we can distinguish into multiple subfamilies. And in the dynamic case, we have, for example, stacked architecture, where we stack recurrent neural networks for modeling the temporal domain with deep graph network for modeling the spatial domain. Or we can have integrated architecture, where we mix recurrent neural network with deep graph networks, and so on. And as you may understood, like there are several works that propose models that can process the spatiotemporal dimension of a dynamic graph. And there is a recent interest in graphs defined through stream of irregularly sampled events, so as continuous time dynamic graphs. And typically, these methods are based on a static deep graph network and recurrent neural network as backbone architecture, as I said before. And this means that they retain their limitation, the same limitation as their core components. And specifically, static deep graph networks suffer from the oversquashing phenomena, which prevents the final network to learn and propagate long-range information. And similarly, recurrent neural network often face similar challenges in propagating long-term dependencies, mainly due to exploding or vanishing gradients. So both deep graph network and recurrent neural network forget long-range dependencies. But why exploiting long-range interaction is so important? Because in some problems, the exploitation of local interaction between nodes is not enough to learn representative embedding. Indeed, a specific problem typically needs to consider a specific range of node interaction in order to be effectively solved. And so we need a specific number of layers that is possibly large. But despite the progress made in recent years in our field, many of the proposed methods still cannot learn long-range information. For example, if we consider this graph, and in particular the red node, the more the layers, the more the information is routed into its fixed length encoding, resulting in an annihilation of the long-range information. And so in this case, the model demonstrates a dissipative behavior, and it exhibits a convergence of node features, node embeddings towards non-informative values as we add more layers. So learning effective information propagation patterns still remain a critical challenge that affect the final performance. And so here we aim to propose a novel and general architectural bias to deepen our theoretical understanding of deep graph network and to develop a more effective and versatile model that is capable to preserve long-term spatiotemporal dependencies between nodes and to learn complex spatiotemporal patterns from irregularly sampled data, so from continuous time dynamic graphs. So here we present continuous time antisymmetric network, which is a new framework based on stable and non-dissipative ODEs for learning long-range interaction in continuous time dynamic graphs. And here stability and non-dissipation are the main properties that characterize our method. And we theoretically prove that the behavior of our method is achieved thanks to the definition of antisymmetric weight matrices. So how do we learn a continuous time dynamic graph as a dynamical system? So learning the dynamics of a continuous time dynamic graph can be cast as a problem of learning information propagation following newly observed events in the system. So it can be modeled through a dynamical system described by a learnable ordinary differential equation. And we can define a Cauchy problem on graphs in terms of a node-wise ODE. And this function describes the dynamics of the node representation in the time span between 0 and t subject to an initial condition. And here sigma is the activation function as usual, and phi is the aggregation function that basically aggregates the temporal neighbor states and the current time and the time of interaction with the neighbors. And thanks to its formulation, we can cast basically any standard deep graph network through our framework. And for example, we can use an aggregation function that is based on an attention mechanism. And by relying on differential equations, we can naturally deal with events that arrive at arbitrary time. And so basically we can learn from irregular data by dividing the problem into multiple subproblems, and in particular one for each event. There is one subproblem for each event. So each subproblem is responsible of propagating the information of an event between two consecutive timestamps, subject to an initial condition that here combines the prediction obtained by solving the previous subproblem and the observed state at the current time. And by solving all the subproblems, we obtain the evolution of the entire dynamic graph. So to give you a more clear idea, let's consider this example. So we have this state of this graph, and at some point, we receive a new interaction event between U and V. So now they are connected. So what happened is that we start propagating such information until a terminal time t. And this propagation is, of course, designed as a dynamical system that follows the ODE that you have seen before. So now we know how to learn a continuous time dynamic graph as a dynamical system. And we proceed by deriving the condition under which our dynamical system is non-dissipative. So that allows for the propagation of long-range dependencies in the information flow. But what it means to be non-dissipative? So non-dissipativeness in continuous time dynamic graphs can be dissected into two components, which are non-dissipativeness over space and over time. Over space means that given two nodes, U and V, in the continuous time dynamic graph at some time t, that are connected by a path, if an event occurs at node U, then the information of such event is propagated from U to V, regardless of the distance between the nodes. And over time means that if we have a node U in the continuous time dynamic graph at some time t, and the node is subject to one event, then our system is non-dissipative over time if, regardless of how many more events will occur at U, the information of that particular event will persist in the embedding of the node. So basically, the node retain its complete past. And so a non-dissipative propagation, we know from theory that is directly linked to the sensitivity of the solution of the ODE to its initial condition. So it's directly linked to the stability of the system. And such sensitivity is controlled by the Jacobian's eigenvalue. Indeed, for example, if the real part of the eigenvalues is greater of the eigenvalues of the Jacobian is greater than 0, then the resulting system is unstable. While if the real part of the eigenvalues of the Jacobian are very less than 0, then what we have is a lossy system where long-range dependencies among nodes are forgotten. And lastly, if the eigenvalues are very close to 0 or exactly 0, then we have a non-dissipative behavior. So a system that is capable to propagate long-range dependencies. And if we employ antisymmetric weight matrices, then the resulting eigenvalues are placed exactly on the imaginary axis. And so we achieve a stable and non-dissipative behavior over both space and time. However, the initial condition still plays a crucial role for the property of non-dissipativeness over time. Because if we use a dissipative function, for example, that discards completely the solution of the previous subproblem, then we cannot propagate the information across time. So now we have defined the condition under which we can learn a continuous time dynamic graph as a dynamical system, and we can define a dynamical system to act in a non-dissipative way. However, we observe that computing an analytical solution for an ODE is usually infeasible. And so it's common practice to rely on a discretization method that computes a solution iteratively over a discrete set of points, between the time of the event and the terminal time of the propagation. And we, in our experiments, we employed forward Euler method to discretize our differential equation. And this equation represents the discretization of the system, where epsilon is the step size, and gamma is a term that preserves the stability of the discretized system. And here we provide the full picture of our framework, continuous time antisymmetric network, where each event is propagated across the graph as a non-dissipative dynamical system. And this behavior is achieved by employing antisymmetric weight matrices and non-dissipative initial conditions. And if we employ the forward Euler as discretization method, then we obtain this discretized propagation equation. So now coming to the experiments, to assess the theoretical behavior of our approach, we so that our continuous time antisymmetric network is non-dissipative, we designed two novel temporal tasks which require the propagation of long-range information by design. And these are label propagation on a temporal path graph and a temporal interpretation of the Pascal-Vogt task from the long-range graph benchmark for static graphs. And then we show the capabilities of our framework on 8 classical benchmarks, including TGB, temporal graph benchmark. So the first task is that of label propagation temporal path graph. So the idea here is that we want to propagate a label from one side to another in a temporal path graph, which is basically a path graph where we add a new node at each timestamp. And here we report the accuracy, so the higher the better, with respect to the length of the graph. And as you can see, state-of-the-art approaches fails almost immediately in solving this task, and they reach the performance of a random guesser after a few steps. And this is because basically the information is lost through the time steps. While our method here in green shows robust performance across various graph sizes. And this I highlight its capability to effectively propagate information across the graph. And the second task that we propose for long-range interaction is the temporal interpretation of the Pascal-Vogt dataset proposed in the long-range graph benchmark to show the efficacy in capturing long-range interaction in static graphs. So in the static case, this dataset is composed of graphs created from images. And in each graph, nodes are superpixels that are connected with adjacent superpixels. So each node is in a graph corresponds to one region of the image that belongs to a particular class. And the task is to predict the class of each node. And in the temporal case, we consider that nodes appear from the top left to the bottom right of the image sequentially. And so this is similar, like if we were scanning the image from the top to the bottom. And to do so, we selected the top leftmost node, and then we traversed the graph through a BFS. And so, and in particular, we visited each node exactly one. And by doing so, basically, we removed a large number of edges from the initial graph, making the propagation of the class information even more difficult. And so I'm forcing to and so enforcing more long-range interaction in the graph. And then we forward edges one at a time to the model and predict the class of the destination node. And so here we report the F1 score. So again, the higher, the better. And we report results with multiple layers or discretization steps in the case of our method. And we report results for two versions of the datasets that consider different sizes of the regions to predict. So we can have more patches, which means that the superpixels are smaller, and so we need to propagate more information across the graph in order to effectively solve it, or fewer patches, which is basically the opposite. So we have less long-range interaction. And as for the previous task, our method has better performance than literature approaches, except if we consider one-up of convolution in the dataset with fewer patches. And this is because since there are less nodes, there is also there is partially closer relevant information that compared to the case of more patches. And this is basically why digiformer has a comparable performance to our framework. However, if we allow our framework to explore larger neighborhood, then we outperform digiformer even in that task. And so now we move to the last part of the experiments, and where we consider real-world benchmarks. And on the left, we have four tasks proposed by Kumar et al. So we have Wikipedia, Reddit, Last.fm, and Mock. And while on the right, we have the TGB benchmark. And so our model shows remarkable performance, ranking first in almost all the dataset on the left. And our method achieved a score that is on average almost 5% better than the other baselines. And also our method is on average 2 times faster on the four tasks. And this finding basically show the importance of non-distributive behavior even on real world tasks. Since we need to achieve good performance, we need to retain and propagate more information. And so these results basically demonstrate that our framework can better capture and exploit such information. While on the right, on the TGB benchmark, we know that our method performs quite well in general, and indeed its average rank across the four dataset is the highest together with digiformer. And also lastly, we noticed that even with a limited number of parameters, our method is extremely competitive within the leaderboard. And so coming to the conclusion, during this talk, we highlighted the role of differential equation-inspired deep graph networks, investigating novel information propagation dynamics, integrating concept from dynamical systems. And we propose a general solution that offers an inductive bias that addresses the challenge of learning long-term spatial-temporal dependencies in continuous time dynamic graphs, while achieving state-of-the-art performance on real-world benchmarks, as well as on tasks that are specifically designed to assess the effectiveness on the long-range interactions. So thank you for your attention, and also thanks to my collaborators, Giulio, Claudio, Davide, and Klaas.
Yeah, great. thank you for your presentation. I think there are some questions in the chat, but thanks for the very clear and nice presentation and uh, like
Thank
walk us
you.
through your paper. Um, so I have a question there, but if the audience you would like to ask your question live, feel free to jump in as well. Um, so can you go back to the experiment section? So my
Yeah.
question was about the temporal path uh,
Yes.
experiment you were doing. So like the performance is very good here. Uh,
Mm-hmm.
it does start to decay like after 15 to 20. So this is, I suppose this is some sort of numerical instability, or it's because the discretization you are doing. Like, can you explain like how do you like expect this to work in the longer and longer like graph size?
Yeah. So basically, I think here I think the performance started to degrade because of the discretization that we use. Basically, as I said here, we intro. Can you see my pointer?
Yeah.
Okay. We introduced this new term for making the forward Euler stable again. Uh, because the stability region of the forward Euler is slightly different from the one of the dynamical system in the continuous domain. And basically, what the effect of this term is basically to push the real part of the eigenvalues more on the negative side. And so basically, you start dissipating a little bit.
Hmm.
And and so what happened is that um, if you have this value too big, then you are pushing a lot the eigenvalues towards being dissipative again. And and so basically what happened here is that probably by playing with that parameters, because it's an hyperparameter at the end, um, we can make the model more or less dissipative. And so maybe we can push up again the performance of the model.
Okay. So it depends on hyperparameter choice, basically.
Yes, exactly.
Okay. Interesting. There's also like another question from the chat. Uh, it's mostly talking about the repeated size of the graphs you were doing for your experiments. Yeah, and because the tables are too small to read from the slides.
Here,
Yeah, and also the one you were doing for the Pascal, it's not clear what how big the graph sizes are.
okay, the graph sizes. So here in for TGB and the classical benchmarks, uh, graphs are pretty big, especially in TGB. We the Wikipedia is the smaller one with hundreds of thousands of nodes, and comments is the biggest um, with yeah. Here I actually don't remember how many nodes there are, but uh, and maybe Andy, you developed it, so maybe you can answer better than me.
Check
Uh,
from the paper, but the comment is also not the largest in terms of number of, I'm not sure about number of nodes, but it's not the largest in terms of number of edges. So there are larger graphs with more edges, but
yeah,
they are
but still, this is like pretty huge. Like we had, um, I think we had some issues in running this
of course.
uh, DGPL comment because it was pretty big, and so it was like kind of the edge of out of memory error all the time while we were running experiments.
So
Uh,
what largest size like tensor do you need to process in your method? Like, well, like which part does it go out of memory? Is it the discretized snapshots or
no, I mean it's just because. like storing the entire graph in the memory, uh, if the graph is very big, then you cannot uh, like store it like easily. Um,
I see. I see. So,
because like um, I think that our method is pretty scalable because like for example with respect to TGN, in TGN you need both you need a memory module and a propagation module and a recurrent neural network module. And while in our method, basically you can get rid of the uh, of the um, of the memory module because it's already uh, like inside the behavior of the dynamical system, because the dynamical system stores inside the node embedding like the entire past of the node. Um,
right, I see.
But did you just show that your performance the plot with the performance went up to 20 or 25 nodes, I think? Yeah, there.
yeah.
So after 5 nodes, you're no better than a coin flip. So how's
Uh,
that scalable? I don't understand. I'm sorry.
Sorry, my framework is the green line here.
Oh, okay, okay.
All the others are the baseline like TGAT, TGN, Jodi, Graph Mixer, DiRep, and IGFormer. And yes, like you're right. After like 5 steps, basically, they are the same as a random guesser. So like you can flip a coin and it has the same performance as these models here. And this basically reinforce what I was saying, that those methods are not able to propagate information across longer radii.
I don't want to play devil's advocate, but you're talking about dynamical systems. Those are known to be non-robust, very sensitive, very computationally costly, and not scalable. So here you show performance up to 20, and 20 is arguably a very small toy graph. What would happen if you had 200 or 2,000 nodes?
Um, yeah, actually, I kind of disagree with you, saying that graph neural network based on dynamical system are very expensive, because like uh, there are plenty of works that are actually that works pretty well and they scale also pretty well, like Grand, ADGN. Um, I mean, there are plenty of those. And also, I believe that those are even faster because most of the time they do weight sharing. So when you stack more layers, basically you just reuse the weights. Um, and here we just stop at 20 because like already after like 5 steps, all the baselines basically degrade to a random guesser. So we thought it was
Well, I
pointless
think we can
to,
agree the baselines are garbage, but 5 nodes,
yeah.
that's not even worth discussing. But I'm just, you know, any
Yeah.
graph with less than 20 nodes is not interesting to analyze.
Hmm.
You can do
Yeah.
it with a pen and paper. You don't need differential equations.
Yeah, yeah, yeah. But exactly, this was just a toy example to show that baselines are garbage. But when we use like real world benchmarks like TGB and the one from Jody, here we have hundreds of thousands of nodes and millions of edges. So like the graphs are pretty huge.
Yeah.
And I also have a plot of the runtimes. Here we focus just on Wikipedia, and our model is again the green line. and the green line here. And we are kind of the
That's pretty
fastest
impressive.
model,
Yeah.
even if you use 1 layer or 5 layers.
Oh,
Or
cool.
like we can try with even more, but again, like if it works if we are faster with 5 layers, then we are still faster with probably more layers.
Thank you very much. Interesting.
Yeah, thank you.
Yeah, so so definitely very interesting discussion, and thanks for sharing your work. So just curious, what do you plan to work on next in terms of improving your work? Do you want to do
Uh,
more, or do you want to have newer method that, you know, scales better or something? I'm not sure.
yeah, my idea is still try to bridge the theory from dynamical systems with graph neural networks to try to solve this problem that we have of long range propagation. I think that here like we can do better. For example, like first of all, we can improve the discretization method that we use because forward Euler is the easiest one that we have, but we can have something that, I don't know, for example, as a computes a dynamical step size, so the is more efficient in terms of computation and solution. But I think it will be interesting to so maybe like there is this new hot topic that is state space models. It will be interesting to bring state space models in the graph domain.
Right. I think they already work on that, though not tested on the same task and benchmark. I think there's two
Yeah,
dig.
yeah. No, I know. Um, like there are several works on this direction. Still, I haven't seen, and maybe this is a strong opinion, but I haven't really seen a real state space model for graphs because usually is again a graph neural network with a state space model at the end, but
Mm,
not a state space model that is designed to perform a graph convolution.
I see. Okay, I see what you mean. Yeah, that does sound quite interesting. But also we need better benchmarks to benchmark these things, right? Uh,
Yes, of course.
yeah. So, yeah. So thanks for sharing your work and yeah, like very promising research direction to investigate more. Um, and yeah, so let's thank the speaker again, and so we will like wrap up here. And I think for next week it's Halloween, so we don't actually have a reading group. So enjoy some downtime, and then we'll see you after that for the next talk in I think November 7th, right, Julia?
Yep, I think so too.
Okay, great.
Yeah.
Thank you, everyone. Have a
Okay.
great day.
Thank you.
Thanks
Bye
for
Thank
bye.
you very much. Bye.